Okay, let's take a look at the structure of benzene and the general reaction of aromatic compounds, for which benzene, shown here, is an example. These are characterized by rings that have alternating double bonds, and boy, are there a lot of them. You know, you put an N there, they call it pyridine. You put two nitrogens in there, you call it a pyrimidine, and you can go on and on. There's lots and lots of aromatic substances. And this is benzene, probably the grandfather of them all. So we see these alternating double bonds. This is a bit misleading, however, because if you actually scope it out, all the bond lengths are the same. So this isn't a great way to draw it. You might want to draw it like this. If the bond lengths are all the same and it's C6H6, I guess a 1.5 bond order works. This wasn't very satisfying to scientists, and they eventually agreed to say, let's draw it this way, but realize that it's halfway between the double bond being there and the double bond being there. That means that this one doesn't do it, this one doesn't do it, it's halfway in between. We imply that using this double-headed resonance arrow, and we show the electrons migrating in such a way that you're halfway between those two structures. These are the two resonance structures that contribute equally towards the structure of benzene. These are not individual substances, they are representations of the same substance. However, this is the way we draw it, and it's fine because it helps you sort of see the reactivity pretty clearly. These double bonds are electron-rich, meaning nucleophilic, and they can attack things that are electron-poor, meaning electrophiles. So the typical reaction is known as electrophilic substitution, or more properly, electrophilic aromatic substitution. And we're only going to show one kind, and that is nitration. If you want to make a nitrobenzene, you can do that. You better be careful, though, because once you put 3 nitro groups on this thing, it becomes explosive. A very similar substance, trinitrotoluene, is a shock-sensitive explosion. So don't let this thing go too far. Now, this implies a lot of stability, right? These electrons are spread out. Anytime you can spread out electron density, you're going to make a more stable substance because electrons are repelled by each other. So if we're going to break that thing up, we need a good electrophile, preferably something with a formal positive charge. You could try just heating it up in nitric acid, but if you add a little bit of sulfuric acid, and even stronger acid, that'll really get things going. It will protonate the oxygen of nitrobenzene, water can get kicked out, and you get an electrophile of stupendous energy. That is that nitro cation, and the NO2 cation is going to be very susceptible to electrophilic attack, so much so that it can break up that stabilized ring structure. Now that'll electrons come out, imagine them come out almost like a windshield wiper that's still attached to that carbon, to this carbon right here. You'll get a positive charge right there. That positive charge is not shown here, but it's a typical exercise to show what they call the resonance stabilization of it. It's a stabilized one because it's actually spread out both here and here. These arrows do show it. Imagine that double bond swinging in there while staying attached to that carbon. That'll show you a positive charge there. Very reasonable. They can also swing those electrons into there, rendering that part positive. So that positive charge is really distributed throughout 3 regions equally. In any event, this thing can finally lose H+, regenerate its aromatic ring, and you've got nitrobenzene. Just remember, 1 is fine, 2 is fine, 3 is getting super scary. So that's in our quiver of reactions, and in fact it's our only reaction we're going to consider for benzene, electrophilic aromatic substitution in the form of nitration. However, we will show that if you wanted to turn that nitro group down to an amino group, we need to hydrogenate it there, and so that can be done with just tin and hydrochloric acid. Tin is your reducing agent. It will get oxidized probably to tin oxide, and you'll get amino benzene. Since it's acidic, that nitrogen will protonate, and it will give you what's known as a quaternary ammonium salt. So this is an ammonium, 4 bonds on your nitrogen, so it has a positive charge. And I'd like to point out here something that students so often don't really get. When you have a positive charge, that's a salt. That'll go into the water layer. So analynium chloride or aminobenzene in the form of the HCl salt, for example, will be water soluble, and you can get it to remove it easily by just, it's now a water soluble salt, goes into the water layer. The rest of your stuff typically doesn't, all your other organic stuff, and you can separate it out. But maybe you don't like it like that. Maybe you like it not as the quaternary ammonium salt, but as the free base. No problem. Just react it with hydroxide. That'll pick up that H+, remove some water, and you now have aniline, formerly known as aminobenzene. And so this is a sequence to turn benzene into aminobenzene. This is an introduction to aromatic compounds.